So today we're going to start looking at some theoretical probability. Okay, so essentially we're finding probability using our combinations and permutations. Okay, so combinations and permutations, the whole point of that was that you were counting how many different possible outcomes there were for a given sample space. Okay, so what we're going to do is we're going to use combinations and permutations to find two separate values that we can divide, right? And probability, remember, is the number of ways to get a favorable or desired outcome divided by the total number of possible outcomes. Okay, so essentially what we're going to do is we're going to do two different combination or permutation problems and then divide them to find our probability of something happening. Okay, so let's take a look at this first one. Okay, so in this first one, we are looking at a basket of tomatoes. It's got 9 using pesticides and 11 that were grown organically. If you randomly select 3 tomatoes, find the probability that 2 of them were grown using pesticides and 1 is organic. Okay, so we're going to look at the number of ways to get our desired outcome, which in this case is that the 2 of them were grown using pesticides and 1 is organic. Okay, so we're going to find the probability of having 2 with pesticides, right? 1 organic, right? And to do that, we're going to set up a fraction here. So the fraction on the top part is going to be the number of ways to get what we want. Okay, so we're starting up here with the number of ways to get 2 with pesticides and 1 organic. Okay, so that's how we're going to kind of start this. And on the bottom, we're going to look at the total possible outcomes, right? So this is going to be the total number of ways that you can just pull those 3 tomatoes out. Okay, so 2 separate problems. So this top one, right? I'm going to have 3 slots because I'm choosing 3 tomatoes. Okay, we want the first 2 to be grown with pesticides and then the last one to be organic. Okay, so there were 9 with pesticides, so it would be 9 times 8, and then 11 grown organically, so times 11. But the order in which they're selected doesn't matter if you're just pulling them out of the bin, right? Doesn't matter what order you pull them in, we just care about the end result. So I'm going to have to divide by 2 factorial because these 2 could have been swapped, right? All right, so I'm going to go ahead and calculate that number. So 9 times 8 times 11, and then divided by 2 factorial, or 2. So that's 396. Okay, and now we're going to go back and calculate our total number of possibilities. So total possibilities is just pulling any 3. And there's a total of 20 tomatoes in the bin, right? So I'd have 20, 19, 18. Just pulling any 3 tomatoes. But again, the order doesn't matter. So we're going to divide that by 3 factorial. Okay, so 20 times 19 times 18, and then divided, I know 3 factorial is 6, so I'm just going to do divided by 6. So that's 1140. Okay, and that is what we're going to use to calculate our probability. So our final probability is 396 divided by 1140, which is 0.347 or 34.7%. And there we go. That's the probability that this will happen. All right, cool. Let's take a look at the next one. So a corporation has 8 men and 6 women on its board of directors. At the meeting, 7 directors are seated in a row on a platform. So seated in a row, we're talking about a particular order. This tells me it's a permutation, right? Directors are chosen and assigned a seat in random order. What's the probability that they're arranged? There's a key permutation word. In a sequence so that men are in seats 1 through 3 and women are in seats 4 through 7. Okay, so we're going to do the same thing. So I'm going to set up my giant fraction here. Okay, and in the top, we're going to look at the number of ways to get what they wanted. So the number of ways that you have 1 through 3 are men and 4 through 7 are women. All right, so let's take a look at this. So we're going to have 7 slots. 5, 6, 7. We want the first 3 to be men and the last ones to be women. There's 8 men to choose from, so 8, 7, 6. 6 women to choose from, so 6, 5, 4, 3. Okay, and like we said, this is a permutation, so the order matters. Okay, so the order matters, so I'm not going to divide by any factorials. I'm just going to multiply these numbers together. So 120,000. So that works out to 120,960. Okay, so that is the top part of my fraction. So now I'm going to go back and do the bottom part, where the bottom part is going to be the total number of ways. Okay, so we have 7 seats. But now we're not restricting it to men or women in any particular place. We're just saying if you just scattered them randomly. So there's a total of 14 people, right? So it would be 14, 13, 12, 11, 10, 9, 8. Okay, and again, we're arranging them in an order. So I'm not dividing by any factorials because the order matters. All right, so I multiply all that together and I get this really big number. So it looks like 17,297,280. All right, excellent. And then that is what I'm going to divide to find my probability. So 120,960 divided by that answer works out to 0.006. Okay, so it's 0.00699, right? So in terms of rounding that, right, if I'm trying to round to this decimal place, this one would tell me to bump it up, which would tell me to bump that up. So it'd be 0.0070, right? Or 0.7%. So pretty unlikely that this would actually happen. All right, and then the last one, what's the probability that you will get tails 3 or more times if you flip a coin 4 times? Okay, so 3 or more times. That's kind of the tricky part here. All right, so let's take a look at this one. So we're going to set this up again. All right, and we're looking for, on the top, the number of ways to get tails, so 3 or more tails. All right, and for this particular problem, the easiest way I think to do this is actually to kind of list them out. Okay, these kind of heads and tails problems, these ones are a little bit tricky when you want to establish that you're going to have 3 or more. So 3 or more basically means 3 or 4 in this case, right? So the easiest way to kind of do it with these ones would be to count. So like if I wanted to have just 3, right, tails, then it could be tails, 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 heads. It could be tails, tails, heads, tails. It could be tails, heads, tails, tails, or heads, tails, 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 right? And the ways to get it 4 times would just be obviously all tails. So there's 1, 2, 3, 4, 5 different ways that this could happen. Okay, so our ways for this to happen would just be 5, and I'm not really worrying about figuring out all the possible, like how to figure this out using a permutation. Sometimes with these ones, for right now at least, it's just easier to count. We could also look at this and say, calculate this a little bit differently and think of this like, remember when we did those winning versus losing a series of games, or when we rearranged the words? We could also look at this and say, well, pretend this is a 4-letter word, right? TTTH. So there's 3 of the same letter. So we could look at it and say, well, there's 4 factorial ways to reorganize it, but 3 of the letters are identical, right? And then calculate it that way, you get the same thing, 4 outcomes here. And then that would obviously just be 1 outcome. So either way, you're going to get your 5 outcomes. But that one can be just a little bit tricky to sort of think about. Okay, on the bottom, when we're looking at the total number of ways, okay, this one is a little bit easier to approach because we're flipping a coin 4 times and there's 2 options for each one. Okay, so that's just going to work out to 16. So just something about figuring out ones where it's like heads versus tails. It can be a little bit tricky to calculate them. Like you can do it, you can calculate them. You have to do it by cases, right? Which we've talked about before. So you have to use it by cases, but I don't know. Sometimes if it's a small enough group, I think it's just worth it to do it out the other way. All right, I pop that into my calculator. That works out to 0.3125, so a 31.25% chance of that happening. All right, and that is the idea of probability using permutations and combinations. Okay, now really quick, one thing that I want to point out to you. When you're doing these problems, you really have to pay attention to whether they are permutations or combinations. And there is a particular danger. Problems like this, right? So if, say instead, this had said you wanted 3 with pesticides, so it would be 9, 8, 7, and we divide by 3 factorial, right? So if the factorials were the same top and bottom, you get the same answer whether or not you divide by those factorials. Okay, so in terms of putting it in your calculator, they are still supposed to be there, but it won't affect your end answer because it's a common factor top and bottom, basically. Okay, but in a situation like this one where it wasn't the same factorial, you do get a totally different answer if you include them and then if you don't. Okay, so one of the things that I see people mess up is they don't pay close enough attention to whether or not they should be dividing by factorials here, and that can really get you into trouble. Okay, because sometimes you'll still get the right answer even if you forget to put them there, and that can really like hurt you in the long run. So just be careful that you're really like paying attention to those things and watching out for your details.